Welcome back to the second lecture of this course. And before I start, I want to say something. Now, you might see that that's a ridiculous thing to say. Before I start, I want to say something. It's self-referential. And I'll be coming on to that later in this talk as one of the tipping points in mathematics, where things start referring to themselves and getting contradictory. But I did want to make just one other comment before I actually start the lecture. That book, The Number Sense, has a tremendous amount about how we view numbers in our lives, number notation, number language, numbers, how they worked out in the brain, and things like that, by a French neuropsychologist who is extremely good on this subject. There's been a lot of work being done on how people think mathematically. I'm not going to get onto issues like are girls better than boys at mathematics? That's one of the issues. But that is a wonderful book to get hold of and read. I know that it's in Jagger Library. But I want to start way back with the origins of mathematics. There's a little bit of a baboon bone, it's about that long, found in a cave in the Lubombo Mountains, South Africa in other words, and it's inscribed with 29 notches. It's 30,000 years old, and it's the oldest example of the recording of a number. Because whatever it is, that must be they were counting something on that bone. Now, one can speculate a bit with these bones that are found in other cultures, certainly in the Congo, and you can speculate a bit about what the notches mean, and you can actually add far too much to your interpretation that could have been in the mind of a person who cut those notches. It has been said that because there are 29 notches, that's a calendar stick, because calendar sticks like that are used, or have been till recently used in the Kalahari by the San clans. Again, in South Africa, we have that ochre tablet. Blombos Cave, not far from us, of course, and that was dug up fairly recently, and it's inscribed quite precisely with parallel lines and triangles and things like that. 100,000 years old. Fairly reliably dated as well, that ochre tablet. So here you have the oldest examples of a numerical idea and of a geometrical idea, and the oldest examples in the history of mathematics, and they're right here in Africa, in South Africa. Well, people would be collecting these ideas as cultures develop, and it's only when you start putting them together that things become interesting. Otherwise, they're just a hodgepodge of numbers or designs or something. And that's how math started, as a collection of simple processes, but no attempt to find relationships between them. So with no connections, there could be no conflicts. But only when an attempt is made to systematize the accumulated knowledge is there a chance of noticing contradictions or conflicts with the corresponding need to look closely at the underlying mathematical structures. This lecture is therefore going to explore some interesting crises, which I've called tipping points in the development of mathematical ideas. So we start with Pythagoras. Well, virtually nothing is known about Pythagoras. He's a figure of legend, lots of stories about him. Most of the stories date from hundreds of years later. There was, it seems, a brotherhood round about 600 BC, and let's suppose that their leader was this man called Pythagoras. Round about 600 BC, at the same time as other great thinkers, religious and philosopher thinkers, such as Confucius, Buddha, Lao Tzu, and the Old Testament prophet Isaiah, in different parts of the world, all thinking deeply about theology and philosophy, and of course unconnected. Round Pythagoras there grew a secretive religious cult which believed that chaotic nature could be understood through numbers, which are therefore worthy of worship. Now, Pythagoras is said to have discovered the elements of harmony, for example, by listening to the note emitted by a plucked string or plucked strings of different lengths. But if you take one plucked string and you just pluck it, it emits a note. If you halve its length, it emits a note 1 octave up. If you divide the string in the ratio 2:3, you get a perfect fifth, and other ratios like that will give you the harmonies that everybody recognizes in music. This is due to Pythagoras or the Pythagoreans. Sorry, there's a lecture here. You'll have to stop. There's a lecture right here. I'm lecturing. You'll have to stop. Okay. All right. I didn't mean to broadcast that exchange to everybody. Well, there was a brotherhood of Pythagoras, but this law of music came up. Interesting. It's the first exact mathematical, numerical law of physics ever. Now, there'd be laws of physics like if you drop something, it falls, or the sun comes up every day, or something like that. The first exact law of physics is the Pythagorean discovery of harmony. And it's a wonderful discovery. If that most abstract of subjects, music, can be explained by whole numbers and simple ratios, so can the whole world. There is order in the universe, and that order is described by numbers. And this discovery has, of course, been the model of scientific thinking ever since. Numbers and geometry, as we saw in these two bones, numbers and then geometry, unconnected, they come together at the time of Pythagoras. In the observation, for example, that if you take the sequence of odd numbers, 1, 3, 5, 7, 9, and add them up, 1 plus 3 is 4, 1 plus 3 plus 5 is 9, add 7, it's 16, you get a perfect square every time. Now, if you just think of that numerically, adding up the sequence of odd numbers and you get a square, you'd say, well, that's very interesting. But when you see it geometrically, it's obvious. And this interplay between geometry and numbers is just so important to the Pythagoreans. There's a similar one. If you take the numbers, just add the numbers 1, 2, 3, 4, you can then make equilateral triangles out of them. 1 plus 2 plus 3 plus 4 is 10. 10, this is the holy tetractus of Pythagorean theology. They had prayers to the tetractus. Doesn't seem to have a following these days. But what about the famous theorem of Pythagoras? The most important achievement credited to Pythagoras is the theorem about right-angled triangles, which everybody knows. In fact, if you ask them anything, what do you know about mathematics, they'd say, oh, the theorem of Pythagoras. And they might even be able to state it correctly, namely that the square on the hypotenuse is equal to the sum of the squares on the other two sides. Well, how did that come about? Well, it's quite conceivable that Pythagoras or Greeks were looking at a square floor like that, and let's look at this triangle here. And here, the pattern gives you the square on the long side, the hypotenuse. And it's equal because there are 4 of these half squares. It's equal to the sum of the squares on the other 2 sides. So there's a very simple example of the theorem of Pythagoras, which anybody may notice on a tiled floor. Of course, it's a very specific case because it's a triangle with... I've lost my dot, there it is. With equal size, an isosceles triangle. But in general, if you have a right-angled triangle and you draw the square, then on the hypotenuse, the longest side, then it's equal in area to the sum of the squares on the other 2 sides. It's called the theorem of Pythagoras, and Pythagoras may have discovered it, but if he did, it was only a rediscovery because it had been known for a long time, maybe 1,000 years before, because, oh, by the way, there's no documentary evidence that Pythagoras ever wrote about it or knew about it or anything. It's legend attributes this to Pythagoras. But 1,000 years before, the Egyptians' mathematics had the theorem of Pythagoras. Here is a clay tablet, again about 1700 BC, and here you have a square, and that is 30 up there, that number is 30. So you have a right-angled triangle here, and the square on this hypotenuse. Well, the numbers there are a little bit difficult to see. The lengths there are given as 30 for that side, and then in Babylonian notation, the length of that side is 42 and something. And these are fractions given as 60ths. So that is 42 and 25 60ths plus 35 over 3,600. And then the figure above that line is the ratio of that number to 30. Now the ratio of sides, if you had a triangle of side 1, then the hypotenuse would be the square root of 2, because the square on the hypotenuse is the sum of the squares on the other 2 sides. So 1 plus 1 is 2, and hypotenuse has a length of root 2. So here we have the Babylonians showing the square root of 2, and this number here, in terms of 1 plus 24 60ths plus 51 over 3,600 plus 10 over 3,600 times 10, 71200, is the square root of 2, accurate in our terms to 6 decimal places. 1700 BC. So the Babylonians certainly knew the theorem of Pythagoras and could do that calculation. I'll get back to that one. This tablet, which is much harder to read, gives whole lists of right-angled triangles, the sides of right-angled triangles, which are whole numbers. So the famous 3-4-5 triangle is an example. 5 squared is 3 squared plus 4 squared. 5, 12, 13 is another one. 13 squared is 5 squared plus 12 squared. And that this list here gives a whole string of triplets of numbers known today as Pythagorean triplets, which are the sides of right-angled triangles where the sides are all whole numbers. So the Babylonians certainly knew Pythagoras' theorem way back. Let's just get back to this. As I said, if you're taking this triangle here, this is the square root of 2, and that is 1 and 1. Now, the Pythagoreans had done all these wonderful calculations with whole numbers, and they allowed fractions into their system because fractions are just ratios of whole numbers, but they were rather horrified to discover that when you have this figure, and that's 1, and that's 1, and that's the square root of 2, and then the square root of 2, if you're a Pythagorean, must come out as the ratio of whole numbers, because everything was number. And they were devastated to discover that there is no whole number with, there is no pair of whole numbers where the ratio is the square root of 2. Now, there are various ways of proving this, geometrically or numerically, but what I like to do is just show you that it's really quite simple to believe, because if the square root of 2 is m over n, then n times the square root of 2 is m. And then if you square both sides, you get m squared is equal to 2n squared. And at that stage, you just look at that long enough and you realize that that can't be. Now, you could be complicated about this, but I prefer to say it this way. It's a basic fact of numbers, these being whole numbers, that you can express a whole number as a product of its prime factors. So 30 is 2 times 3 times 5. It can't be expressed in any other way other than rotating or altering the numbers. And 1001 is 7 times 11 times 13. There's no other way of expressing a number, 1,000. There's no other way of expressing 1001 as a product of prime factors in any other way. So every whole number has a unique expression as a product of prime factors. So m is expressible as a product of prime factors. On the right-hand side, therefore, you have a list of prime factors repeated. So on the right-hand side, you've got an even product, even number of prime factors. Similarly, for n, there's an even number of prime factors there. But if you have that 2, how can that be that an even number of prime factors on that side could be also expressed as a product of an odd number of prime factors on the other side? Just can't be. Odd can't be equal to even ever, and that wraps it up. Pythagoras and Euclid had another way of showing that, which is perhaps more complicated in some ways. But in fact, what I was invoking there in giving you that little argument is the result that a number can express, any number can be expressed in only one way as a product of prime factors, because that turns out to be really not quite obvious, although most people would accept it as being intuitively clear. Well, this argument that I've just given you, saying, well, if this is expressible as a ratio of whole numbers, then in a couple of steps we arrive at a contradiction, or what eventually became listed in the classic Latin textbooks, reductio ad absurdum, argument by contradiction, a fundamental method of argument in mathematics and, of course, in logic. So this doesn't work, and Pythagoras, no, he wouldn't have said QED at the end because he was Greek and not Latin, but there is a opera de I think it's something like that. In Greek, and would be in Greek letters, quod erat demonstrandum in Latin is the triumphant cry at the end of every theorem that you manage to prove. So this is the first of our tipping points. unable to conceive of a continuum of real numbers with these irrational numbers sort of wedged in between the rational numbers. You can think of the rational numbers lying along a line, but wedged in between them there's numbers like √2 and others which can't be expressed in terms of rational numbers. And that's worrying when your religion says that everything must be whole numbers or rationals. Well, this bothered the Greeks, so what they tended to do is avoid the problem and think a bit more about geometry rather than numbers, or when they did numbers, they thought about whole numbers. And it wasn't really resolved until much later. The irrational numbers could be considered as geometrical lengths. So then the Greeks did lots of geometry, and they found strings of interesting facts about mathematics. For example, if you draw a semicircle like that, and then you draw that angle, then that is always a right angle, the angle in a semicircle. So they were stringing together these facts. But it was Euclid, a couple of hundred years after Pythagoras, who had the profound impact on the development of mathematics in collecting all these results together and setting them up in a logical order based on a handful of basic background assumptions, geometrical and assumptions about how we reason, to show how everything could be done and established, proved mathematically and rigorously from a very simple set of axioms. 5 axioms and a few propositions, and this Euclidean approach became the model for the development of a mathematical discourse, and is the same with science. And even thousands of years later, Isaac Newton wrote his Principia Mathematica in the style of Euclid. And that style is still preserved today when doing geometry at school. But there came another tipping point at that time. The Greeks, for philosophical reasons, believed that you should restrict yourself to straight lines and circles because they were the perfect figures. They were perfect and ideal. So Euclid's geometry focused on what could be constructed in terms of straight lines and circles, namely ruler and compasses. Euclid showed in elegant style how to do geometrical constructions using only those implements. And so all you've got is a ruler on which you can draw straight lines. It's not marked in any way, so you can't measure with the ruler. And you can draw circles. So if you draw an angle like that, with ruler and compasses you can bisect that angle. And it's a very simple little thing. You put your compass there and you draw this arc of a circle like that. And then you put your compass with the same length, you put compass there and draw that arc and that arc. And then you, with your ruler, you draw that line, and those two angles are then seen to be equal. And why are they equal? Well, Euclid would point out that we've constructed a couple of triangles. These two, sorry, not there. Those two lengths are equal. Those two lengths are equal. The middle line is common to the two triangles, so the two triangles are exactly the same, and therefore the angles are the same. So having done that, the natural thinking is, well, what about dividing an angle into 3 equal parts? Trisection. And If you give this to a class, they say, oh, we'll do something like this. Let's start off like that and mark off those 2 points, and then join that line there, and then divide this into 3 equal parts. Those 3 parts are equal. And you can do this with ruler and compass also, by the way. And then it looks, then you say, well, there we are. We've trisected that angle. But the next step is to show why those 3 angles are equal, and this is where you fall down, you fail, because that's not a valid trisection. It's roughly right, and for small angles it's pretty good. But supposing your angle was quite big like that, and you draw this line across, and those 2 are equal, and then you draw 3 equal segments there, it's then pretty obvious that those 3 angles are not equal. So this construction method works roughly for small angles, but certainly doesn't work for big angles. So it's not a trisection. It doesn't work. You can't trisect an angle. Well, the Greeks tried. They came up with all sorts of plans for trisecting angles, all sorts of gadgets, but they could never come up with a way of trisecting an angle using their rules, ruler and compasses. If you allowed a marked ruler, yeah, you could do it. If you allowed other sorts of gadgets, you could also do it. But ruler and compasses would not trisect an angle. So they didn't even, the trisection of an angle is something they found they couldn't do. They were trying very hard. It's not mentioned in Euclid, which is a great pity because in 1900, a very interesting result was discovered. If you take this man, Frank Morley, you take a triangle and you trisect the angles down there. So at each vertex, those 3 angles are trisected. And then you draw these trisection lines. Then what happens always, in the middle there, you get an equilateral triangle. There's no reason to suspect that you should. It's a surprising and rather interesting result. It's not impossible to prove for a bunch of high school kids, but I'd take about a lecture to do, and 2/3 of a lecture to do it. But the Greeks missed it. Why? Because ruler and compasses said, trisection is not allowed, we can't do it, so they didn't come up with that result. So that's 20th century result in geometry by this man, Morley. Well, there were other things that the Greeks tried to do related to trisection. There were 3, in fact, famous problems. And one was the trisection, which is over here. Another one was if you have a cube, so this is a 3-dimensional problem. Now, it arose from, so the story is of the god Apollo demanding of his followers that the cube altar dedicated to his name was not big enough and it should be doubled. So the worthy populace said, okay, fine, so you just double each dimension, but that actually was multiplying the volume of the cube by 8. And the Apollo's wrath descended upon that temple, and they suddenly realized, oh, we've got to construct, if this cube is of length 1, then we've got to construct another cube where the length of the side would have to be the cube root of 2. So although you can construct the square root of 2, which is what Pythagoras' theorem showed us, how would you construct the cube root of 2 given ruler and compasses? And they couldn't do that. And the third problem, the third of the 3 famous problems of antiquity, which had influence for on the development of mathematics for thousands of years. The third one was given a circle to construct a square which is exactly equal in area to that circle. Squaring the circle. And that's a metaphor now of doing something impossible. Well, you can't square the circle with ruler and compasses. There are gadgets with which you can square the circle, but the Greeks couldn't do it. And it took thousands of years before it was worked out why. So these simple geometrical problems were tipping points that had a profound effect on the development of mathematics. There's how you would construct a square root in general. The square root, if a and b are two numbers, you construct that circle, semicircle, and the perpendicular is of length square root of AB. And I want to come back to that little observation later on. But Euclid's postulates, the basic assumptions on which the whole work is based, were these four simple ones. To draw a line from any point to another point, to produce a line as far as you'd like, to describe a circle, and then a blindingly obvious one that all right angles are equal to one another. Those are four of his postulates, but the fifth one, even when you look at it, it's longer, and it says, if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, will meet on that side of which are the angles less than the two right angles. It's far more complicated than the first four. In terms of a picture, it's saying that if you've got two lines like that and you mark those two interior angles, if they come up to be less than two right angles, then they will meet, the lines will meet over there somewhere. And if it come up as more than two right angles, then the lines will meet over there. And this is the parallel postulate, which turns out to be absolutely crucial in Euclid. But because it is so complicated, compared with those postulates, people said, hang on a moment, surely we could just derive this from the previous four. Why do we have to put this complicated statement in? Surely it's a theorem, not a postulate. But in fact, nobody could do that. So the parallel postulate was something that vexed mathematicians for thousands of years until in the 19th century, people said, well, hang on a moment, if we deny that, how much geometry can we do? And they invented things called non-Euclidean geometry. There was a Hungarian Bolyai and a Russian Lobachevsky who did this, and another man, a German Riemann. They developed these non-Euclidean geometries, which are fanciful things because, obviously we live in a Euclidean world, and surely these things are just figments of the imagination. Well, they weren't. Non-Euclidean geometry was exactly what Einstein needed for his four-dimensional geometrical description of the universe. Well, that was then a tipping point, and it inspired the tipping point of the parallel postulate, kept mathematicians going for thousands of years, and gave them new directions to investigate. Moving on now to the Quattrocento, which you remember is the 14th, 15th century in Italy. Fantastic flowering of mathematics in Italy, including the development of algebra. Before then, algebra was very complicated. The idea of symbolic algebra and the notation that we have derives from Italian mathematicians who did a great deal of work. By the way, at the same time, Italian mathematicians invented something which also had a profound effect on the economy of the world, namely double entry bookkeeping. It comes from the same time, the same sort of people. Well, the Greeks and the Babylonians had effectively been able to solve these things called quadratic equations, algebraically written like that. The Greeks and the Babylonians had to express them in terms of geometry, but they could essentially get to that formula expressed geometrically by a method which is done in school called completing the square, and that is standard school stuff for the quadratic equation of where the degree of the highest power, x there, is 2. Well, they said, let's try and take equations where you have not an x squared but an x cubed in it. And these had been around for some time. The Babylonian mathematicians considered simple cases. Also, Omar Khayyam, whom I mentioned yesterday, the Persian mathematicians considered this so-called cubic equation, but it was the Italians who cracked it. There's quite a romantic and complicated story about the solution, but here is the general cubic equation, the cubic equation over there, and here is the formula for its solution, which is a formidable thing compared to that one. They do that in school, they don't do that one, for good reason. You can do this at school level. It requires a great deal of very muscular algebra, and then you can bang it out. The point about the formula is that it involves squares and products and plus and minus and square roots there and cube roots. But just with those four basic operations of arithmetic plus square roots and cube roots, you could crack the general cubic equation. That was a major achievement by Italian mathematicians in the 14th, 15th centuries. They then said, well, now, okay, let's go on to the next level, the fourth degree equation, where you've got an ax to the fourth, and they managed to crack that as well. But then they got stuck on the fifth degree equation. But before going on to that one, something strange happened in this analysis. They'd get this formula, and you'd have an equation where you could see right from the start that the equation has nice simple roots. But when you applied the formula, over here, you'd get a square root. And then the bits inside there might turn out to be negative. And you'd have this idea of the square root of a negative number, which doesn't make sense. The same term occurs in the second part. This is the same term here. There's a plus there and a minus there. So this could be a square root of a negative number. They said, how can that be? Nevertheless, they soldiered on because it worked. So you just carry on with your calculation as if, never mind that these things were not real, they were imaginary numbers, but everything came out. So this concept of an imaginary number came up, which people could not actually explain. The square root of a negative number. So here you have, say, 1 and negative 1, and do that square root calculation, and it comes up there, that length there. And the inspiration is to think of that square root of a negative number as extending numbers from a one-dimensional concept to 2 dimensions. So now you have these imaginary numbers expressed as 2-dimensional things. And now they're called complex numbers. They're not complex. And I is called an imaginary number, which it isn't. It's perfectly real in that picture over there. So that was a problem and was another tipping point. But just to get back to the Italians having cracked this cubic and the fourth degree equation, they tackled the fifth degree and they couldn't do it. So for the next couple of 100 years, nobody could find a formula for solving a general fifth degree equation. Now, solving would mean producing a formula like that, where all you're allowed to use in your formula are plus, minus, multiply, divide, square roots, cube roots, fourth roots, and fifth roots if you're going to quintexent, but nobody could do it. Nobody could find a formula in those algebraic terms which would solve the general fifth degree equation. And eventually it was found and shown to be impossible. Now this is interesting. How do you show that something is impossible mathematically? How do you show that it's impossible to trisect an angle? Have you tried everything? No, of course not. Maybe it's not so obvious if I say it's impossible to find two odd numbers which add up to an odd number. That, if you think about it, is not so difficult as an impossibility idea. Well, the Italians couldn't do that, and their successors in Europe into the early 19th century couldn't crack it either, until a young mathematician by the name of Abel, of whom more to be said later, showed that you can't get a formula for that fifth degree equation. And at the more or less the same time, a very romantic figure, Évariste Galois, French, did much the same sort of thing in analyzing quintic equations. And both of these two guys, Abel and Galois, died young. Abel at the age of about 27, I think, from tuberculosis. Galois, a revolutionary in the 1830s, got himself involved with a woman and a duel, shot in the intestines, died of peritonitis, aged 20, having discovered a fantastic amount of stuff which is still being worked on today, and there's a whole area of mathematics called Galois theory. My next postage stamp is, in fact, an attempt to continue with this idea of complex numbers, but further on. And this man, Rowan Hamilton, an Irish mathematician, came up with this idea of extending complex numbers which are two-dimensional to hypercomplex numbers which are four-dimensional. And he had this idea of constructing this theory of numbers which he called quaternions and of using them in physics. And he was a great promoter of them. He was sort of partly right. They are useful in physics, but they haven't really been incorporated into the study of physics. So the Irish commemorated this discovery, the 100th anniversary of the discovery, in 1943 with a halfpenny stamp. Is that all they could afford? But later on they came up with the 29 pence stamp, and these are the basic formulas that Hamilton discovered for his four-dimensional things called quaternions. Very interesting. There was subsequent development of people saying, well, why not go up to more dimensions than four? And the next one was octonions, at 8-dimensional numbers, which sound, interesting, but, why bother? Well, string theorists today have a use for these 8-dimensional numbers called octonions. Yet another example of a piece of pure mathematics which is useless at the time you invent it, but gets application much later. Just getting back to Ireland, the first president of the Irish Republic, Eamon de Valera, was a mathematician, but he'd gone into politics, and of course at that time fairly violent politics, but never mind. He was the first president, much revered in Ireland, but still a mathematician at heart. If you read John Gunther's Inside Europe, written in the 1930s, he relates the story of how Eamon de Valera would expound the theory of quaternions to any unsuspecting aide who happened to be within earshot at great length and exhaust them. But quaternions is an interesting word. It's a word that appears in the Bible, in the Acts of the Apostles. St. Paul is put in prison, and a quaternion of soldiers is designated to look after him. Of course, he breaks out, and there's a bit of a fuss. But that's where the word occurs. And there are not many mathematical words in the Bible. Well, of course, be fruitful and multiply. So multiply comes up. But mathematical words are at a slightly higher level, like quaternions. You won't find equations in the Bible or anything like that, the word equation. But there is one other mathematical word that occurs in the Bible, not used in a mathematical sense, a good quiz question. And of course, when I say the Bible, I mean the King James Version. And people usually don't know this. It's in a couple of obscure places in the Bible. And the word is matrix. Now, matrix algebra was something invented in the 19th century, enormously important in today's commerce and industry and physics and chemistry and everything. And a matrix is an array of numbers which is manipulated in various ways. Well, you'll find, if you look up in a concordance, you'll find the word matrix, and you look it up. But it has a meaning which you might expect from its etymology, mater, mother. A matrix means a womb. So you'll find a matrix in the Bible, and you'll find quaternions in the Bible, but few other mathematical words. After the Italian Renaissance, we go straight to Isaac Newton's monumental Principia Mathematica, and now I've put him there again. And that's got his discoveries, but one discovery that's not in that list, or not in the picture, is Isaac Newton's discovery or invention or creation or codification, whichever word you like to use, of the calculus. And calculus concerns itself with finding areas and slopes and lengths of complicated curves. So if you've got a curve like that, what is the slope of that curve at this point there? What is the slope of the curve there? Well, if you draw a chord of the curve, the slope of the chord is the ratio of that line to that line. That's the slope. But that's an approximation to the tangent, the slope of the tangent. So if you make the chord shorter and shorter, you'll get closer and closer to the tangent. So if you make the chord of zero length, you've got a tangent. But then, of course, your ratio is 0 divided by 0, which is now a little bit controversial. But Isaac Newton did all this and was not able to get hold of this idea of these vanishingly small ratios. But nevertheless, his calculus worked. Now, the philosophers, notably famous Bishop Berkeley, was a great opponent of calculus. He says it's not logical. He was quite right. The way Euclid set it out and his contemporaries, it was just not logical. And the problem was that this calculus stuff worked. And people just carried on doing it because it worked. And they pushed aside the philosophical objection to these vanishingly small quantities that disappeared, and yet they somehow retained a reality. But this is actually quite a very subtle idea, these limiting ratios. And I want to give you an example that I always give my first-year students to think about. You've got a picture here, and I've got this train steaming down a track at 100 kilometers an hour, and a bee flying up in the opposite direction at 1 kilometer an hour, and they meet. Moment silence for the bee. The bee is, of course, immediately squashed. The train doesn't deviate from its speed, doesn't even notice. Now, question. At the moment of impact, what is the speed of the bee? Before impact, the bee is going along at 1 kilometer an hour. After impact, the bee, rather smeared over the front of the locomotive, is traveling in the opposite direction after the impact, is traveling in the opposite direction at 100 kilometers an hour. What is the speed of the bee at the moment of impact? So it was 1 there, but the bee is attached to the locomotive. It can't be at 0 because the locomotive, it's attached to the locomotive, and the locomotive is going at 100. So it can't be 0. 99 and a bit or something. It's a problem. It's a problem which I usually like to leave my students with and suggest that they try it on with their parents at dinner that evening. But this leads on to the subject of limits and infinities. And it was in the 19th century that this investigation of these limits to try to unravel that sort of problem really took place. And the concept then arose of infinity and how you handle that. Now, infinity does not exist in the real world. All real-world sets are finite. After all, there are only 10 to the 70 atoms in the universe, a large but finite set. We think of infinity as a very large number, or we think of infinity as an enormous length, or we think of infinity as a place where the parallel lines meet. So these different ways of thinking about infinity are quite challenging. And it was only in the 19th century that these ideas got sorted out. And one of them, I like to think of infinity in that way. It's an idea invented by mathematicians. It's an idea. Infinity is only in our minds. It's nowhere real. It turns out that there are levels of infinity. And there was a man by the name of Georg Cantor, 19th century. He died almost 100 years ago this month. That, of course, that is the classic symbol for infinity, the sideways 8. He came up with this idea, an analysis of infinity, and he showed that if you think of the whole numbers, they're infinite, and if you think of the real numbers, including all the extras like irrationals, they also form an infinite set, which is essentially larger in a way that he made quite precise. So you've got these two infinite sets, the whole numbers and the real numbers. Is there a level of infinity between those two? So an infinite set which is essentially larger than the set of whole numbers, but essentially smaller than the set of real numbers in a precise way which you have to spell out. And nobody could prove that. And this became known as the continuum hypothesis. Could you find a set of numbers which are more than the whole numbers and fewer than the real numbers? And nobody could prove that it was true. Then in the 1930s, an Austrian mathematician by the name of Kurt Gödel showed something quite important. Gödel on the right, of course, with a pal at the Institute for Advanced Study in Princeton, the founder member, namely Einstein. Gödel was a very strange mathematician, genius. He actually showed that if you took the continuum hypothesis and assumed that it was true, you would not, let me just get this quite right, because if you assume that the continuum hypothesis is true, Gödel said, you would not be able to get a contradiction. So you can't get a reductio ad absurdum by assuming that it's true. And then later on, some 30 years later, a man by the name of Paul Cohen proved that no contradiction would arise if you assumed that the continuum hypothesis is false. So this result is undecidable. It's a statement that can be clearly made in terms of the mathematical structure that's there of numbers, but you can't say whether it's true or false because you can't prove it true and you can't prove it false. So what does that mean? It means that you could add this continuum hypothesis to your list of axioms and get a new, richer type of mathematics. So it's rather like the parallel postulate. The parallel postulate can't be proved true or false, but if you add it, you get Euclid's geometry. If you add a variation on it, you get other types of geometry. These problems were undecidable. But at the same time of considering these issues, philosophers were trying to rewrite mathematics in a totally logical way. And this idea, this paradox, is due to Bertrand Russell. Now, in the English language, let's think of adjectives in the English language, like the word English itself, which describes itself. English is an English word. So is Afrikaans. Afrikaans is an Afrikaans word. But French, of course, is not a French word. Now, it's easy to think of words that are that don't describe themselves, like long is not a long word. So you can produce a whole list of adjectives. This is quite a nice game. Think of words, adjectives in English, that describe themselves. So how about unhyphenated? Or polysyllabic? Well, I think that's enough examples. And you can put any number of words on the other side. Hyphenated would go on this side. It is not a hyphenated word. So Russell said, now let's give these classifications a name. So we'll call these words homolytic, and we'll call these heterolytic. And every word should fall into one of those two categories. It either describes itself or doesn't. Well, where do you put that word? It's an adjective. I mean, we just invented it, but it's probably in the dictionaries by now. It's an adjective. Is it a heterolytic word? I mean, should heterolytic be on this list? Well, if heterolytic is a heterolytic word, then it describes itself, so it should be on that list. Okay. Well, if you write it on this list, then heterolytic is a homolytic word, but hang on. And then it doesn't describe itself. So the self-reference thing leads you to all sorts of paradoxes, which is why I said at the beginning, before I start, let me say something. So this required mathematicians and logicians to go back to the foundations of logic and spend some time sorting it out. I think I want to say just one other area, because this leads to, there are two big areas in mathematics, one in applied mathematics and one in pure, that I want to mention as basically important tipping points which are really focusing the attention of mathematicians. And the one is quantum theory. Now, quantum theory is very strange, and yet it works. I mean, that's why this gadget works, because there's the quantum physics behind it. The quantum theory was devised by various mathematicians. One of the foremost developers was a man by the name of Werner Heisenberg, who came up with this uncertainty principle, which says that if you're trying to gauge the speed and the position of an object, you can't get both to a very high degree of accuracy. The higher accuracy that you get for the position, the worse your accuracy for your measurement of speed, or the other way around. Sorry, something's happening here. Okay. But it turned out that this was a fundamental issue in quantum mechanics which had to be accepted. And there's an example of it which came up on the program Top Gear when one of the drivers was evaluating a racing car, a high-performance sports car, and he said it had this wonderful geopositioning dial on the front which showed you exactly where you were, but you had to press a button to get from your speedometer to the location device, and you couldn't get your speed and your position at the same time on that particular Freud. And that's really what quantum theory is telling you. But the really big problem that is bugging mathematicians to this day concerns prime numbers. Those very simple things in mathematics. I want to get past these guys to this man, Bertrand Russell. I don't have time to talk about the other ones. The investigation of prime numbers leads to a hypothesis called the Riemann hypothesis, after this man, Bertrand Russell, who, by the way, was one of these people doing non-Euclidean geometry in the 19th century. And the most famous unsolved problem today is known as the Riemann hypothesis. It's a key issue in understanding the erratic distribution of prime numbers. Its importance was pointed out by Riemann in the middle of the 19th century and has remained a stumbling block in mathematics to this day. Now, it's difficult to explain the significance of the Riemann hypothesis, or indeed to explain in simple words what it says, or why it is important. But it concerns the so-called Riemann zeta function and where it is zero. And it was set out at the beginning of this millennium as one of the major millennium problems by the Clay Institute in America, for which they are offering $1 million for reward. So the Riemann hypothesis is the number one problem in mathematics today. If you can crack it, you'll get the $1 million and a lot more besides, in terms of recognition and invitations to go to all sorts of interesting places. So much so that it has moved somebody to poetry. It concerns the Riemann zeta function and where the thing is zero. And somebody wrote, oh, where are the zeros of zeta of S? We must know exactly, we cannot just guess. In order to strengthen the prime number theorem, the integral's contour must not get too near them. So that's the Riemann hypothesis, unsolved for 150 years so far. Question, is it perhaps undecidable? I don't think anybody thinks that it's undecidable. A lot of mathematicians think that it is not true, but nobody's been able to prove it, and nobody's been able to disprove it. It's a big tipping point in mathematics, and mathematics thrives on tipping points. Thank you. Questions over there? I beg your pardon? Yes.
The numerical system that we know today, when did that replace the Roman numbering system?
Oh, the numerical system. Well, that was again Italian, and you can date that to 1202 almost precisely. It was a man by the name of Fibonacci of Pisa, and he wrote this book on using the decimals, the decimal system, as opposed to the Roman system. The merchants were not happy about that because the decimal system, when you think about it, can be easily forged. You can change a 9 into an 8, or you can change a 1 into a 7, and they much preferred writing numbers in Roman numerals, especially cursively. So it took some time for that system to be accepted, but it was 1202. Fibonacci, who is also famous for a problem about rabbits, which is a whole new story. But that's when that happened. Yeah?
I think the principle of uncertainty, which was discovered by Heisenberg,
Yeah.
applies to subatomic world, not molecular.
Oh, yes. Now, in fact, I wasn't able to get onto this, another big area of mathematics. The principle of uncertainty applies to the subatomic world, not to racing cars. But in fact, the quantum theory then deals with the microscopic world of the atoms. And at the same time, Einstein had come up with the theory of relativity, which deals with the huge cosmos, the macroscopic world. And Einstein and others thought, well, we've got two theories that don't look like each other, but they